A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Here's what Daniel sent us this week. He wants to dig into the deeply technical side of voice agent UX. Not TTS quality, not transcription accuracy, but the conversational dynamics underneath. Specifically, how agents handle interruptions when a user talks over them. How they detect when a user has actually finished speaking versus just pausing to think. What the latency budgets look like across the full pipeline. And what happens when you blow them. How agents maintain conversation flow while they're off fetching data from some external system. And finally, the state of emotional and prosodic awareness in 2026, whether voice agents can actually read the room. 5 topics, all connected by the same core question: why does talking to a voice agent still feel slightly wrong, and what's actually being done about it?
This is one of those topics where the hard part is invisible to almost everyone using these systems. The perception is that voice AI is basically solved. Transcription is good, voices sound great. But the failure modes Daniel is pointing at are where the real engineering is happening right now.
And I'd argue most developers building on top of these platforms don't fully understand the failure modes either. They're using Vapi or LiveKit or Pipecat, and they've got the default set, and they don't know what's actually going on underneath.
By the way, today's episode is powered by Claude Sonnet 4.6, our script writing AI of choice this week.
Alright, let's start with interruption handling because I think it's the most viscerally familiar problem. Everyone has had that experience of trying to cut off a voice agent, and it just keeps talking at you.
So the naive architecture is voice activity detection, VOD, which listens for the presence of audio energy from the user and triggers a stop when it detects it. The detection itself is fast, 50 to 100 milliseconds. The problem is, VAD is completely dumb about what it's detecting. It cannot distinguish a genuine barge in the user actively trying to take over from a back-channel acknowledgement like uh-huh, or right, or okay. Those are fundamentally different conversational acts, and VOD treats them identically.
So the agent stops mid-sentence because you said to show you were listening.
Every time. And then it's waiting for your next input, and you're waiting for it to continue, and there's this awkward silence. That's the failure mode. Now, the 3 platforms Daniel mentioned handle this differently in ways that reveal a lot about their design philosophy. Vapi has the most publicly documented interruption system. They have a T-stop speaking plan with 2 modes. The first is VAD-based, fast but dumb, as we said. The second is transcription-based, where the system waits for a configurable number of transcribed words before it decides to stop. So you set num words to 2, and the user has to actually say 2 recognizable words before the agent yields. That buys you 200 to 500 milliseconds of delay, but it cuts false positives dramatically.
That's an interesting design choice. You're trading response speed for accuracy in the interruption detection itself.
And Vapi also has what they call tacknowledgement phrases, a list of words that, when detected, tell the system to ignore the interruption entirely. Okay, right? Got it, If you say any of those, the system treats it as a back channel and keeps talking. That's a meaningful step towards solving the back-channel problem, even if it's a list-based heuristic rather than a learned model.
LiveKit takes a completely different approach, right? Less opinionated.
LiveKit is the opposite end of the spectrum. They describe themselves as the Legos of voice AI. They expose the full framework and let developers configure turn-taking to their specific needs. You can set allo interruptions directly. You can call interrupt explicitly in code, and you can build custom logic around when handoffs happen. They also use WebRTC selective forwarding units rather than WebSockets, which gives you better packet loss handling and scalability. Their smart endpointing uses a sigmoid curve wait function, a mathematical formula that returns wait time in milliseconds based on speech completion probability. You can tune it aggressively for fast response or conservatively for careful response.
The sigmoid curve is interesting. It's not a fixed threshold, it's a continuous function. So at 50% confidence that the user has finished, you might wait 200 milliseconds, but at 90% confidence you're already down to 50 milliseconds.
That's the aggressive configuration, yeah. The conservative version adds seconds of wait time at lower confidence levels. The point is that LiveKit gives you the knobs, Vapi abstracts them. And then Pipecat is the open source option, BSD2 clause license, and their approach is their smart turn model, now at version 3.2.2. It's a Whisper Tiny backbone with a linear classifier layer, about 8 million parameters, available in a CPU version at 8 megabytes quantized and a GPU version at 32 megabytes. It runs in as little as 10 milliseconds on some CPUs.
8 megabytes for turn detection. That's remarkably small.
It's small because the backbone is Whisper Tiny, which is already a tiny model. But the key thing SmartTurn does that PureVAD doesn't is it looks at prosodic cues, pitch, intonation, speaking rate, rather than just audio energy. It waits for 200 milliseconds of silence from Celero VAD, evaluates whether a turn shift should occur, and if confidence is too low, it defers the decision. If silence persists for 3 seconds, it forces the transition anyway. That fallback is important. You don't want the agent waiting forever because it couldn't make up its mind.
So VAD is the trigger. Smart Turn is the judge.
Crisp has entered this space too with their Viva SDK, a 6 million parameter audio-only turn-taking model optimized for CPU inference, operating on 100 millisecond audio frames. They benchmarked it against SmartTurn versions 1 and 2. Crisp's model achieves a balanced accuracy of 0.82 versus SmartTurn's 0.78, and more importantly, 0.9 seconds means shift time versus 1.3 seconds for SmartTurn at the same false positive rate. 30% faster at equivalent accuracy while being 5 to 10 times smaller.
Okay, so let's talk about why turn taking is genuinely hard. Because I think the backchannel problem is the tip of the iceberg. The deeper issue is what Speechmatics calls the thinking pause problem.
This is where it gets subtle. Consider someone saying, "I understand your point, but," and then pausing for a full second while they formulate the next thought. VAD-only systems call that an end of turn. A human listener intuitively keeps waiting. And the consequences in production are worse than just awkward. In finance, customers spelling out account numbers pause between digits. The agent cuts them off mid-sequence. In healthcare, patients recalling a patient ID from memory pause, same problem. Every premature interruption also drives up LLM API costs because you're reprocessing a misinterpreted partial utterance.
And the solution isn't just wait longer, because if you wait too long, you've got a different problem.
The field has converged on 3 approaches to turn detection. Audio-based approaches analyze prosodic features, pitch, energy, intonation. Fast and lightweight works in real time but misses semantic context. Text-based approaches analyze the transcribed content for sentence boundaries, discourse markers, question markers, more accurate but more latency. And then the multimodal fusion approach, which is where Deepgram's Flux model lives.
Flux is interesting because it's architecturally different from bolting turn detection onto ASR after the fact.
The key innovation in Flux, launched late 2025, is that the same model producing transcripts is also modeling conversational flow and turn detection. You're not running ASR, getting text, and then running a separate turn detection model on that text. The turn detection is happening in the same forward pass. That eliminates a significant sequential delay. Their benchmark numbers cuts agent response latency by 200 to 600 milliseconds compared to pipeline approaches, reduces false interruptions by about 30%, achieves P90 latency of 1 second, and they define 2 core conversation native events. Start of turn and end of turn with a configurable confidence threshold called TO threshold TOT.
What's the default threshold?
SIR 0.7. You can go down to 0.5 at SIR 0.6 for aggressive response, higher risk of cutting users off, or up to 0.991.0 if you want the agent to wait longer and be very sure the user is done. They also have something called eager end of turn detection, which fires an eager end of turn event 150 to 250 milliseconds earlier than the standard event, allowing speculative LLM calls. The cost is 50 to 70% more LLM calls. For latency critical applications, that trade-off often makes sense.
Let's talk latency budgets, because this is where the engineering gets genuinely unforgiving.
The magic number is 300 milliseconds. Human conversation has a natural interturn pause of 200 to 300 milliseconds. Research shows pauses above about 400 milliseconds are perceptible, and beyond 1.5 seconds you've fundamentally shifted the user's mental model from conversation to query response. Once that shift happens, no voice quality improvement rescues the experience. The budget breakdown from current production engineering, STT finalization takes 50 to 100 milliseconds. LLM time to first token takes 100 to 200 milliseconds. TTS time to first byte takes 50 to 80 milliseconds. WebRTC transport adds 20 to 50 milliseconds. Total, 220 to 380 milliseconds. That's the window.
And the LLM piece is where you see the most variance by model choice.
Dramatically so. Grok-hosted Llama variants hit 50 to 100 milliseconds time to first token. GPT-4o Mini is 120 to 200 milliseconds. Gemini Flash 1.5 is around 300 milliseconds, which is already at the edge. GPT-4o is around 700 milliseconds. And frontier reasoning models, the extended thinking variants, are in seconds. So the capability latency trade-off is real and brutal. The models fast enough for voice tend to be smaller and less capable at complex reasoning.
Which is why streaming architecture is non-negotiable.
A naive sequential pipeline, wait for full STT, then run LLM, then run TTS, produces 600 to 2000 milliseconds of latency. The production solution is streaming across all three stages simultaneously. Streaming STT emits partial transcripts in 20 millisecond audio chunks, so the LLM starts processing before the user even finishes speaking. Streaming LLM sends tokens to TTS as they arrive. Streaming TTS begins synthesizing audio from the first sentence fragment while the LLM is still generating later paragraphs. Combined savings, 300 to 600 milliseconds over batch processing.
And then transport matters too. Phone calls are a different beast.
PSTN, traditional phone calls, adds 150 to 700 milliseconds of network transit. That's a penalty no model optimization recovers. You can have the fastest LLM on the planet and still blow your latency budget because the phone network ate it. Geographic co-location matters too. A user in Australia hitting a Virginia data center adds 200 to 300 milliseconds of round trip before a single token is processed.
The FDB v3 benchmark from April 2026 is worth getting into here because it shows the full picture across systems.
The full duplex bench V3 from National Taiwan University and NVIDIA tested 6 systems on multi-step tool use with real human audio. Not simple response latency, task completion latency including tool calls. GPT real-time completed tasks in 6.89 seconds. Gemini Live 2.5 at 7.26 seconds. Grok at 65 seconds. The cascaded pipeline, Whisper into GPT-4o into TTS, took 10 to 12 seconds, dominated by an 8.78 second first word delay. And Gemini Live 3.1 was the fastest at 4.25 seconds.
But Gemini Live 3.1 has a problem.
A significant one. Despite being fastest at task completion, it has the worst turn take rate, 78%. It produces no speech at all in 22% of scenarios. And 86% of those silent cases still executed tool calls. The model found the right API to call but never generated speech. The paper calls it a disconnect between reasoning and speech generation. It's concentrated in harder scenarios, 0% of easy tasks, 23.5% of medium tasks, and 46.7% of hard tasks receive no response.
So the fastest system is also the least reliable. Speed and reliability are directly in tension.
Which is the central trade-off in architecture choice. And there's a counterintuitive finding that connects to this. The uncanny silence problem isn't about latency at all. It's about prosody. You can get latency under 300 milliseconds, transcription accuracy is high, the voice sounds good in isolation, and users still report something feels off. Sesame AI's research paper from February 2025, Crossing the Uncanny Valley of Conversational Voice, nails this. Their CMOS evaluation found that when human evaluators are shown generated versus real speech without any conversational context, they show no clear preference. Naturalness is saturated. Modern TTS matches human performance on that metric. But when you give evaluators 90 seconds of conversational context and ask which continuation feels more appropriate, they consistently favor the human recordings. The gap isn't in audio quality, it's in contextual prosodic appropriateness.
The model doesn't know how to speak a sentence given the emotional and conversational history.
That's the one-to-many problem. There are countless valid ways to speak any given sentence, but only some fit a given conversational moment. Without the emotional and conversational context, the model doesn't have the information to choose the right one. And there's also a counterintuitive point. Speechmatics makes about response speed. Agents that respond in 200 milliseconds feel wrong. Not impressive. Human conversations have a natural 600 millisecond interturn pause. That slight delay signals that the listener is processing what was said. This is why Vapi's wait seconds parameter exists. It's a deliberate artificial delay applied after all processing completes before the assistant speaks. Default is 0.4 seconds. Healthcare applications push it to 0.6 to 0.8 seconds. Gaming applications go down to 0.
The field spent years optimizing for speed and is now deliberately adding latency back in. That's a great headline.
It really is. And the self-correction problem from FDB v3 is equally sobering. They tested what happens when users correct themselves mid-utterance. Book me a flight to New York. Actually, make that Boston. Results across all systems. GPT Realtime, the best performer, scored 0.588 pass rate on self-correction scenarios. Gemini Live 2.5 at 0.71. The cascaded pipeline at 0.76, worse than most random baselines. The cascaded pipeline fails because Whisper finalizes the original transcription before the correction arrives, so the downstream LLM never receives the updated intent. Even the best end-to-end models fail on over 40% of self-corrections. This is arguably the biggest unsolved problem in voice agent UX right now.
Okay, function calling. This is where I think most production deployments fall apart in ways that users notice but can't diagnose.
The core tension is that most useful voice agents need to call external systems mid-conversation. Databases, CRMs, scheduling APIs. Those calls range from 50 milliseconds to 500 milliseconds with high variance. The wrong pattern is treating that as a synchronous blocking operation. The right pattern is treating it as an event that needs to be masked. And the FDB v3 paper gives us the most detailed empirical breakdown of how different systems actually handle this.
The filler rate numbers are striking.
Filler rate is the percentage of responses containing a content-free sentence before the substantive response. Something like, sure, let me look that up. GPT, real-time, 16.9% filler rate, 96% turn take rate, 13.5% interruption rate. That's the best overall balance. Brief fillers used judiciously to cover tool execution gaps. Gemini Live 2.5, 829% filler rate, Gemini Live 3.1, 31.7%, Grok 44.3%, Cascaded Pipeline 26.9%, and then Ultravox at 88%.
Ultravox is a cautionary tale.
It's a perfect illustration of how a locally sensible heuristic becomes a global failure. Ultravox almost always emits a filler sentence before initiating the API call. First word latency looks decent, 3.88 seconds. But tool call latency is the worst of any system at 601 seconds because the filler speech fires before the tool call even starts. And because it's speaking when users are still talking, it has a 47.9% interruption rate. Nearly every other response is overlapping with the user utterance. Task completion ends up at 840 seconds, second worst overall.
So the filler speech is actively making the interruption problem worse.
Because the filler speech is happening during the window when users are still finishing their thought. You say, let me check on that, and the user says, oh, and also, can you make it a window seat? And now you've got overlapping audio, the agent is confused about whether it's been interrupted, and the whole thing degrades. Grok's approach is the opposite extreme. It has the highest preemptive tool call rate, 41.6%, meaning it invokes APIs before the user finishes speaking. But it does this silently while letting the user continue talking. So the tool call is running in the background, the user finishes their thought, and the agent already has the data it needs.
But preemptive tool calls have their own problem with self-correction.
That's exactly where Gemini Live 3.1 speed advantage becomes a liability. Its tool call latency is negative 2.27 seconds. It invoked the API 2.27 seconds before the user finished speaking. If the user then corrects themselves, the API was already called with the original uncorrected destination. The data is locked in. The fundamental tension is that the same early processing that makes agents fast frequently locks in outdated user intent. You can't update what you've already committed to.
What does good production practice actually look like here?
A few patterns that work. Pre-fetching predictable data. If you know that at call start you'll almost certainly need to load the customer's account information, fire that request at call initiation before the first user response arrives. Concurrent masking. Acknowledge the request verbally while the API call runs in parallel, generating filler response audio to cover the wait. Threshold-based bridging. If a call exceeds a latency threshold, return a bridging statement rather than silence. Vapi also supports regex-based custom endpointing rules, so when the assistant has just asked for a phone number, you can extend the wait timeout to 3 seconds to give users time to recall it. That's a nice example of domain-specific configuration that generic defaults don't cover.
Let's close on emotional and prosodic awareness, because this is where the gap between technically functional and actually feels good lives.
Sesame's framework for this is useful. They call the goal voice presence, the quality that makes spoken interactions feel real, understood, and valued. Their breakdown, emotional intelligence, meaning reading and responding to emotional contexts, conversational dynamics, meaning natural timing and emphasis, contextual awareness, meaning adjusting tone to match the situation, and consistent personality. Their conversational speech model, CSM, is a multimodal transformer processing interleaved text and audio tokens. 3 sizes, 1 billion, 3 billion, and 8 billion parameter backbones. Trained on roughly 1 million hours of predominantly English audio, open sourced under Apache 2.0.
And their key finding is that even with all of that, contextual prosodic appropriateness still falls short when evaluators have conversational history to compare against.
Their conclusion is honest about it. CSM can model text and speech content in a conversation, but not the structure of the conversation itself. Human conversations involve turn-taking, pauses, pacing, and dynamics that the model has to learn implicitly from data, and even 1 million hours of training data isn't enough to fully close that gap. Their view is that the future lies in fully duplex models that can learn these dynamics end to end.
Vapi's emotion detection layer is interesting in this context because it's a closed box implementation.
Their proprietary orchestration layer includes emotion detection, analyzing emotional tone, and passing it to the LLM as context. The LLM can then adjust its response tone based on that metadata. But developers can't inspect or customize it. That's a deliberate architectural choice. The orchestration layer, which also handles endpointing, interruption detection, backchanneling, and filler injection, is explicitly described as Vapi's core value proposition. It's the one component in their stack where you cannot bring your own infrastructure. Everything else in the Vapi stack is replaceable. The orchestration layer is not.
Which is interesting from a business perspective. The moat isn't the model or the voice or the transcription. It's the conversational orchestration.
And Speechmatics has a useful phrase for the failure mode that all of this is trying to prevent, the uncanny valley of conversation, where interactions feel just human enough to set expectations, but not sophisticated enough to meet them. The insight from their ML engineer, Aaron Ng, is that the most sophisticated thing a voice agent can learn isn't generating sub-200 millisecond responses. It's knowing when to stay silent. That's a reframing that I think the whole field is slowly converging on.
The backchannel problem is worth flagging as genuinely unsolved.
CRISP's roadmap explicitly lists backchannel prediction as a future release. Deepgram Flux's roadmap includes backchanneling identification. Vapi handles it with a static word list. Nobody has a fully learned general solution for distinguishing "I'm listening, keep going" from "I want to speak now" across all the ways humans express those things. That's the frontier.
And the TTS prosody piece, the one-to-many problem. There are countless valid ways to speak a sentence, and the model doesn't have enough context to choose.
11 Labs frames it as a key trend for this year. AI voice agents trained to recognize emotions in speech and adjust delivery accordingly, detecting urgency in a service request, picking up hesitation in a sales inquiry. But even their approach is about adjusting pitch and pacing parameters rather than fundamentally solving the contextual appropriateness problem. The homograph disambiguation issue alone, knowing whether to pronounce lead as lead or lead based on conversational context, is still an active engineering problem.
What's the practical takeaway for someone building on top of these platforms today?
A few things. First, don't leave interruption handling on defaults. The difference between VOD-only and transcription-based interruption detection with a sensible acknowledgement phrases list is the difference between an agent that gets frustrated users and one that feels conversational. Second, the latency budget is more unforgiving than most developers realize, and the constraint is often the LLM choice, not the STT or TTS. If you're using GPT-4o for voice, you're already over budget before the audio even starts. Third, filler speech is a double-edged sword. Used judiciously, GPT, real-time's 16% rate, it covers tool execution gaps naturally. Used aggressively, Ultravox's 88%, it creates more interruption problems than it solves.
And the deliberate latency point. If your agent responds in under 200 milliseconds, add a wait. It will feel better, not worse.
The wait seconds parameter is one of the most counterintuitive features in voice agent engineering. You've done all this work to get fast, and then you artificially slow it down. But the human conversation rhythm is real, and fighting it makes the interaction feel inhuman even when everything else is working.
The self-correction problem is the one I'd flag as most important for teams to understand going in. If your use case involves any scenario where users might revise what they're saying mid-sentence, which is most real conversations, you need to know that even the best systems fail on over 40% of those cases. That's not a configuration problem. That's a fundamental architectural limitation right now.
And the cascaded pipeline's 0.176 pass rate on self-corrections is the strongest argument for moving toward end-to-end architectures even with their other failure modes. The sequential bottleneck doesn't just add latency, it destroys correctness on the inputs that matter most.
Alright, that's a lot of ground covered. This topic is one of those where the more you dig in, the more you realize how much invisible engineering is holding every voice interaction together, or failing to.
Thanks as always to our producer Hilbert Flumingtop for keeping things running. Big thanks to Modal for providing the GPU credits that power this show. This has been my Weird Prompts. If you're enjoying the show, a quick review on your podcast app really does help us reach new listeners.
We'll see you on the next one.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, my weird prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My weird prompts, that's the close from sloth.